Okay, so today, wave particle dualities. So it's to set a stage. So we're gonna talk something called delay choice experiment. And a special version of it is called delay choice quantum eraser. In order to set a stage, we wanna discuss a few things first, okay? Regarding beam splitters and polarizers, right? So we know that beam splitters for classical waves, beam splitters are just beam splitters, right? You get wave in, I. If this is a 50-50 beam splitter, you get half out, and you get half reflected. Correct? So you just kind of split it. Okay. How does this work for single photons? So if you don't, so say this is a coherent state. Okay. How does it work for single photons? Do we get half single photon? I mean, it doesn't even make sense. We cannot have half single photon. Like, this wouldn't make sense, right? So how does this work? Or can it work at all? Yeah? So that's the question that people ask at the early development of quantum optics. And for this, they did an experiment. And I want to give a brief introduction of that experiment, although we are not covering this experiment in our course, in our lab, but this is a very important experiment to know about. It's called Hong-Wu-Mandao experiment. So 3 guys, Hong-Wu-Mandao. I believe 2 of them are Chinese and 1 of them is American. All right, cool. So this is how the experiment goes. They have a source that produces pair photons, just like our BBO pump. So 4, 5, 1, a 10, a 10. Okay. So in our experiment, so now you have all done it. We have 2 detectors here and here, right? What do we get? A correlation that looks like this, correct? At the 0 delay. So if this path is perfectly the same, or if there's no, and there's no extra delay applied to the coincidence signals, we get a high count when there's 0 delayed, right? And when the delay is enlarged, they become more and more uncorrelated, and they approach 1, which is just the behavior of typical lasers, right? So yeah, typical lasers have photons that are kind of uncorrelated, random. All right. So this is what we did, and this is what Ambry Brown, twist C. When they first built the experiment, they saw a correlation, not anti-correlation. They saw a peaked correlation, right? Enhanced correlation. And they call this photon bunching. Okay. Now, what Hong-Wu-Mandao did is they put a mirror here and here. What this does is that, and they put a beam splitter here. Okay. Like that. Yep. They put a beam splitter here. And let me see. Oh, wrong way. This is a very tricky beam splitter to draw. Okay? So they have a photon coming in to the beam splitter after they have photon coming in from another beam splitter, right? What would you expect from the classical wave? And of course, they aim the detector slightly different. So just in order to receive the output photons from the beam splitter. Okay, so you have this and you have this. Okay, bear with my drawing; it's not great. What do you expect for classical waves? Huh? Yeah, I would say so too, right? So this plus this, right? This plus this, right? So one beam gets split by two beams, and the other beams get split to two beams. And these two beams recombine, right? And yes, they might interfere with each other, correct? But when you do, but now we're not detecting, like right now we're detecting the correlation, and we're not detecting. It's not a single detector count that we care about. It is the correlate. It is coincidence. It is the coincidence that we care about, right? So, and of course, for interference, you can always have a little delay somewhere so that you have kind of balanced count on both ports, right? So in that case, we really have this. So the same count. So you probably expect something like that intuitively, yeah. But what they saw is this. They saw a dip that's almost zero, no correlation or no coincidence. Why that? That's pretty strange, right? That is kind of counterintuitive. We see a dip. I mean, if this is a single photon and you go through a beam splitter, if this is a true single photon, if this is a true single photon and you go through a beam splitter, and there are two channels, right? So either you have so this is the channel. This is called channel 1. This is called channel 2. Okay, 1, 2, or better, I'm just call it A, B. A and B, channel A and B. Okay, you either go through the first port, second port, or you go through the first port. Right. So if you measure this, of course you're not gonna have coincident counts because the photon can only be detected by one detector. Once this detector detects the photon, it annihilated. It's gone. Right. So you will naturally expect this, right? But now we have two photons, at least one here. They got fit to here. What's going on? Why do you still see a dip? Right? So this is like feeding the other port. So one photon give you a dip. If you fit in another port, another photon, still give you a dip. What is going on? So that's a little puzzle they have at the time. Okay, Hongwu Mandao. This is Hongwu Mandao. Okay, and you see this is kind of strange because what did we do? We simply just arrange. We don't change anything about the source. We simply arrange how we detect it. We just place this at a little different angle and insert a few optical elements. the mirrors, and the beam splitter, right? So how can our arrangement of detection or observation, how can we change? Why the way we observe changes the outcome? Yeah. So just keep that in mind. It is kind of puzzling. So without giving like further theoretical explanation, just the phenomenon itself is puzzling. Okay, agree? Okay. So I just want you to have a little feeling about how this wave particle puzzle impact people at the early stage of the development of quantum optics. It still is, but the puzzle becomes more and more subtle. That's all. Not the same puzzle. Of course, we have explanation for this. Okay. So this is how it works. And so it turns out that the beam splitter behave a little different for single photons. No. So okay, let me rephrase. So it turns out that the beam splitter also have quantum mechanical properties, in the sense that you always the port that is not occupied. So if you have a beam splitter and you only send one beam here, you don't have this port does not have input, right? But the vacuum field will do stuff, and that affects how the beam splitter works, right? Because of this bosonic property of photons. Okay, so you might say, I will give the derivation later. But so you might say that when you have a photon here and a photon here, the bosonic property of them, the bunching effect, will cause them either to go together this way and not this way, or they will go together this way and not that way. They will stick together. Okay. So on the surface, you could just say that, oh, it is the photon bunching effect, and the photon just love to go together, right? All right, but this doesn't work for the I mean, if you replace this by the laser, just the coherent state, you have like so many photons, right? It doesn't work for that, right? You cannot say that, okay, this two of them will bunch, the two beam will bunch together, and they will only exit on one beam and not the other beam, not the other port. This just doesn't happen, right? So how does the beam splitter work quantum mechanically that make a difference between these two outcomes, the outcomes of two input single photon state or two input coherent state? Okay, so let's try to go over the derivation a bit. All right, so this is what we're gonna do. We're gonna name this 1, 2. So port 1, 2, and 3, and 4. Okay, and this is our beam splitter. And we're gonna use the raising and lowering operators to represent the appearance of a photon in this port and the annihilation of the photon in this port. Okay, so let's give a rule, although it might not be essential, but let's give a rule that when you have a reflection, you pick up a pi/2 phase. The wave function pick up a pi/2 phase, which is I, when you have a reflection, when you do this. Okay? So under this construction, we have one, if you have a state that, so we're gonna just, I'm sorry, let me just call this A, B, C, D, it'll be better, it'll be easier. A, B, C, D. Okay, I don't want to confuse you. So if we have one photon in the A port, right? How does this gonna go here and there? Well, first, we know that it will go like this. It will be a superposition. If it goes this way, D, then it will pick up a phase. If you go this way, C, if you just transmit, it will not pick up a phase. Right? Right. So this is what we will expect. And for B, it's the same. If you go through, if you just go through, there will be no phase, right? You just go through. But if you get reflected, you'll pick up a phase. Okay? All right, so the transformation works like the following. This is a creation operator on the A port over the vacuum. Okay, so now the vacuum is a vacuum of 4 ports. It's a product state of all ports. Yeah. So this is that, and this is this. Can you see that? Right. What I did is simply just convert this to the creation operator acting on the vacuum, and the creation operator will act on the C port. Yeah. So this is not hard. This will give you this relation, this transformation. Okay. Okay, so sand apply here. A, D, I, A, C. A, B. Okay. So from these two equations, we will derive how AC and AD, so the output ports, how the output ports depends on the input ports, right? This is just algebra. Yep. Let's do that. So I'm gonna take AC. Okay, I'm gonna do let me take out this first. So if I multiply this by I, this will become minus 1, right? And I subtract this by this. Okay. If I subtract this, then I'll have 2 AC, right? And this will be gone. So it works like this. Right? Okay. Now I want to take out. So that's not giving me that. Now I want to take out AC. So what I did is I multiply minus I. So this will give me minus I, and this will be 1, this is minus I. And I add the 2 equations. AC will be gone, and this will remain. This will be 2, and AB okay. All right. So this is pretty standard in the. Okay. Let me see. Yeah, should be right. Okay. Okay. Now I want you to. What I want you to pay attention is this. If I just have a single photon here, and then I try to see what will come up on the C and the D port, right? Without taking into account of what's going on here, then my operator will probably just be I'll just have this. Yeah, I will not have this terms. And if I don't have this terms, then what I want to say is that without taking into account of the vacuum port here, it just wouldn't work. It just wouldn't work. Okay, let's come back to this example. So we have a superposition of 2 states. Oh, sorry, no, we don't. We have this. We have 1, 1, right? So this is A and B. 1, 1. And this is 1, B. Yeah? Okay. So that's A, and this is B. Right? Now I have four combinations. The first is this, AD, AD. The second, so this and this turn, AC. And AC. Okay. AC and AD. Be careful. Here, where I have an I, and here I have an I, right? So this give me this, A, C, and AD. You see that? These two cancel, and I have 2D with an I and 2C with an I. So this is I, 0, 2. So this is 2D, and I, 2, 0. So this is C, and this is D, C and D. Right? So apparently only 2 states survive. No, I'm sorry. Only the state with 2 photons in the same port will survive. This state give you, what does this give you? So if you just apply that to the field here, this gives you 1, 1, right? And 1, 1, right? And these 2 states cancel each other, or you could say they interfere with each other. Yeah. So what's the interpretation here? So what happened is, what is happening is, so this C here, so this C is, let me see, this C is this C, right? And it comes from A port, right? So that means let me just draw here. That means this process, I have the photon that is from A, and it go through the beam splitter directly to C, right? And the other one will have to go to the D port, right? So that's what this process is. Yep. On the other hand, I have also this, but this C now this C is from here, right? That's why it picks up a minus sign, because it has an I. This C is from here, and this is B port, right? So the other term This 1-1 state is this process. A photon is reflected. The C port comes from the B port, and the other one is this, right? So I have two different states, but because of the phase that I told you about, pick up a phase, right? So the product of this is -1, and the other one has a phase of 1. So these two processes cancel, and you have this dip, right? That dip just shows that you will either have this or this, photons in one port only or photons in the other port only. So the detector will never have a coincident count. Yep. Okay. Right. Yeah. Anyway, this shows that the beam splitter works quite okay. So and if you, I'm not going to go through the math, but if you put in feed alpha, so you have alpha A, alpha B, and you just like have this go through the same math, you will see that you will indeed have half alpha. It will be like this, you'll be like this. You have beams on both ports, just like the classical interpretation. Okay, so that's the first thing I want you to know about. So the beam splitter indeed work. And the funny thing is, if you input a 2-photon state here, right, it will now go like this. It will not go like this. It will go like this. They will kind of spread out. Instead of bunched together, they will spread out. And how do you work? So here you apply this twice, and IAD AC, right? So AD square minus and AC square plus, and you have oh, actually no, you have all of them. Actually, you have all of them. Actually, you have all of them. My bad. You have this state or this state or both. You have all of them. Yeah. But my point is, it doesn't bunch like you would expect. And so that's kind of counterintuitive. What I'm trying to say is, a lot of the early quantum paradox or puzzles are there because we kind of just discuss this quantum concept in a hand wavy way. We don't have a very solid description And so a lot of times concepts just get mixed up together. But if we write them down like clearly, then a lot of times this puzzle just disappear, right? However, you still need to battle with this notion of non-locality, like because a lot of times when this math, what this math represent are not just the machinery. They are only applicable when you have a probability wave that is spread out. So when you are applying this math, you are intrinsically assuming that you have a non-localized, that the quantum entity is non-localized. Okay, and so anyway, let me keep going. So that's how Mandel experiment, and if we apply this to a bunch of bin splitters, so say like in the interferometer setup, so if we have a Mach-Zehnder interferometer or a Michelson interferometer, and we apply this math, we will see that interference of a single photon with itself can work. And that's why the single photon experiment that you did with the Michelson interferometer should work. Yeah, if your alignment is okay. All right. So yeah, because the experiment we're going to discuss involve an interferometer and the polarizer. So I just want to first tell you that bin splitter work for single photons, but in a peculiar way. I need to be careful. And also, does polarizer work for single photons?
Can I just
yeah.
So my direct notation is a little plastic, but is it like the dip in that experiment? Is it just from the negative interference, destructive interference?
Yes. Yes, because this state as such is supposed to give you a bump, right? Because this will give you a constant count, a click in this port and a click here, and in the other port. So you should have a constant count. But now we have two state that are like this, with opposite phase. One is with +1 and the other is with -1, and this state interfere with each other, and then there. So yeah. All right, let's continue with the polarization. Okay, so polarizer are like this. They are polarizer or molecular structures that has directionalities, that has a certain direction, certain axis. And when the E field oscillate perpendicular to this axis, just imagine there are electrons along this big chained polymer molecules. Okay? And if I have, so this is K and this is my H polarization. Okay? So I'm drawing a classical wave K, and this is my polarization, and I'm going to call it H. And I'm gonna give you so this represents a unit vector in this direction. If the E field is oscillating in this direction, then it will not drive the electrons. If it does not drive the electrons, it cannot regenerate the wave as it passes through this material, right? So this will be blocked out. Yeah. But if you rotate this so that they look like this, they align horizontally, then this horizontal polarized wave can drive the electrons on the polymer molecules, and thus the electromagnetic wave can be regenerated inside the material and will continue to propagate forward. So it will pass. Okay. So this will pass and no pass. So that's how polarizer works. Okay. Now, if we have a single photon, right? If we have a single photon, how would this work? The single photon has a well-defined E field. I mean, in order to define this, you need to have an E field that oscillates like this in time, right? And so this regular oscillation will be along some axis in space. That's called polarization, right? But for single photon, the E field is like it basically like this. It does not have a well-defined trajectory like a well-defined sinusoidal trajectory. It's basically like everywhere. It has many the amplitude and the phase of it is has the max the phase. Sorry, let me rephrase. The phase uncertainty is maximum. The phase uncertainty is maximum. That means you cannot maybe this would make sense. The amplitude uncertainty is minimum, but the phase uncertainty is maximum. You know why? Because we have a single photon, right? A single photon means you have like a very definite amount of energy. And how much energy is that? How much energy is that? H bar omega. So we have a very well-defined energy. If we have a well-defined energy, then we have a well-defined amplitude for the E field, right? So we have right. Actually, it probably goes like this. Let me just draw this for now. It has well-defined amplitude for E field, here or here. But now, because the amplitude in the phase space, the amplitude and the phase are conjugate variables. So if you have minimum uncertainty on one variable, then you will have maximum uncertainty on the other variable. That means, so what does phase mean? Phase means you know whether it is positive or negative. Yeah. As the phase goes, the phase specified whether the E field is positive or negative. If you have positive and negative, you have oscillations in a certain direction, right? But now, since our phase is maximum uncertain, it means it can simultaneously be in a positive and a negative value state. So that's why it looks like this. So what I'm trying to say is the E field of a single photon looks very, very different. Okay? That's all I'm trying to say. The E field of a single photon looks very, very different from a classical wave or a coherent state. Okay? Sometimes we just use coherent state to represent a classical wave, although it isn't. Strictly, it is not. But anyway, so how would polarizer work for the single photon? Without a well-defined E field oscillation, how does it work? Well, we know fundamentally that if a photon gets into the material, it can be absorbed or not absorbed, right? So if this is like a measurement that we did to the single photon, then we can say that the single photon is in two states. One is the absorbed state, one is the transmission state, right? And we can assign, just like we assign, we correlate, just like we correlate the direction of the polymer molecule to the polarization angle. We can also say that absorption correspond to one orientation and transmission correspond to the other orientation, right? So what I'm trying to say is that you can basically randomly assign an axis, and that axis is for absorption and the other axis for transmission, and then you can say that this is in the superposition state of these two. There are certain probability when this goes through, it will be absorbed. There are certain probability when this goes through, it will not be absorbed. Yeah. So now the question is, does this work? Does this work with like the classical polarizer? Which means if you rotate this angle, does it change your probability of absorption in the same way that it change the transmitted intensity? So for the classical waves, we know that the transmission intensity of transmission goes like this, right? How do you know my laser is in the polarized state? It's in the well-defined polarized state. Well, if you see this, that means it's in the well-defined polarized state, a linearly polarized state, right? If it's in a circular polarized state, it doesn't look like this. Understand? Okay. If my wave is, if you don't know the polarization of my classical wave, it could be elliptically polarized, it could be circularly polarized, it could be linearly polarized. You don't know, right? But what you can do is you can have this pass through a polarizer, and then you rotate it and you record the transmission, and you see if the transmission follows this, or if the transmission follows this. This will be for circularly polarized. And this will be our circular polarization. And this will be for linear polarization. So that's how you tell that whether you have a well-defined polarized state or not, and whether, because if you don't have a well-defined polarized state, so sometimes your laser could be incoherent in terms of polarization, right? Like the sunlight. Yes, sunlight does not have a well-defined polarization state. It just kind of just jump randomly, right? So if you apply the polarizer to sunlight, you get just this, a flat line. Okay, so no polarization, unpolarized. So how do we know that a classical wave has a well-defined polarization, and it does? What kind of polarization it is? We use a beam splitter and we just rotate it. No, sorry, we use a polarizer and we just rotate it and see how the transmission goes with the polarizer angle. Yeah. Okay. And this is, by the way, this is called Malus law in classical. So before people know anything about the polarization, people know that light is electromagnetic wave. Therefore, light has polarization. Before people know about this, this is only known to men until Maxwell come along, right? Maxwell is the person who connect the two concepts together, electromagnetic wave and light. Before him, people don't know what light is. They don't have a theoretical description of light. They have a very, very fuzzy idea of like what light is, okay? But at that time, this man, Malus, it should be this, Malus. He did an experiment and he found that the transmission goes with the polarized angle as cosine theta square or sine theta square. Okay, now coming back to here, I said that yes, I mean, this is just a very generic definition, right? If I have the single photon go through any material, I can define a absorption state and I can define a transmission state, right? Absorption means it will not come out. It will be absorbed in the material. Transmission is it will not be absorbed. It will just come out, right? So this is a pretty generic definition, but well, the question is, if I have, so this is the probability, there's certain probability in transmission and there's certain probability in absorption. And because this is the amplitude, I'm gonna just put a square root over it, okay? So if the question is for a polarizer that works for a classical wave, if I rotate it, will this affect my transmission probability in the same way as in the classical, in the same way for as for classical waves? Yeah. And now you have all done the experiment. What do you find? Is the answer yes or no? No, you have not done the experiment. You have not done the experiment yet. You guys have done the experiment. Do you remember?
This was experiment number 6, right?
I don't know, maybe. Or 5. I don't know. Do you remember doing this experiment? What do you find? Yeah, the question is, of course I can just have single photon going through any material, and I define an absorption state and a transmission state, right? This does not mean when I rotate this, the transmission probability. So here I put the detector, and the detector will tell me what is the transmission probability, right? Is it guaranteed that when I rotate this thing, when I rotate the material, my transmission probability will follow the classical Malus law? Is it guaranteed? Of course it's not. I mean, if this is just I don't know, like a glass, you rotate the glass, do you expect anything will happen to your transmission intensity, like your counts, your transmission count? Do you expect anything that will happen to it? I don't think so, right? So apparently it is not a guaranteed property. So that's why I'm saying, okay, then if it's not working for all materials, that when I rotate, this will follow it. The transmission probability will change as I rotate this material. Then, at least for the material that will have a transmission dependence, something called polarizer. If I take that material and I do it here, will that give me the same? Would that give me the same trend in my transmission as a function of its rotation? But each count is, it's like you get one photon at a time, right? And sometimes you don't get count, sometimes you get count. And this just means when you rotate it, you get more count at some angle, and you get less count at the other angle. So we don't really have a theory for this. Okay. The only way we can find out is by experiment, and therefore I'm asking you this question. You have done experiment. What do you find? Okay. All right, that's fair. How about you guys? Do you do Malus law? Do you see the same trend as the classical dependence? Sinusoidal? This goes to from minus to plus. You have a minus count. Oh, so you mean you have? Do you mean that you have something like here and then you just go like this? It doesn't go down to 0. Do you mean that you have some kind of DC? Okay. Okay, if you reach 0, you cannot be just sinusoidal, right? Okay. By the way, if you have something like this, right? It looks like a very sinusoidal thing. And it is a sinusoidal, but it is also a square, just a half angle. So remember, if you have this is cosine square. So a sinusoidal, if you see a sinusoidal signal, it is the same as the square signal. You just need to count the periodicity a little different. Okay? All right, so the answer is yes. Yes. Polarizer works for single photon just as it will work for classical wave. Okay? But here the interpretation is a little different. Here it's not because I have an E field that is, that is well defined. I don't have a E field. Anyway, here it is because the probability, the projection of probability in absorption and transmission. Anyway, it is 1 hour, and I'll give you 5 minutes to refresh yourself and get waters. Okay.
So there's no system clearly for the
Single photons.
Yeah.
Single photon polarization.
Is that because we only follow like that was also given by the manual.
Right.
We follow and we try to like believe it. So
It is assumed.
Oh.
Yeah. It is assumed that it will project to this state and that state. Right? But why should it? Like I said, yeah. Okay, maybe it is fair to say that, okay, this is oscillation in one plane. So if you have no definite phase in this oscillation, you can still have your E field limited in one plane. Okay, that would be fair to say. That's okay. But we don't know that, right? We don't know if that is true. I mean, we don't know. We know what we know for sure is that it will not oscillate sinusoidally. You'll be in plus and minus value at the same time, and you don't know what it is. So certainly, when this work, when the single photon field interact with the molecule, it does not drive it like this. It's like, yeah, it's like plus one and minus one together. So it is the analogy is not parallel. It's not a direct. There's no direct analogy here.
I mean, considering the like what people know nowadays,
Mm-hmm.
we still don't have theory on this. Is it so? Because
We take this as an experimental fact. And because of this experiment, we know now that what characterizes a mode is not only K, but also something called. Remember, I told you. Remember, I told you that mode is characterized by 3 numbers: K1, K2, KXK, right? KZ, right? And the operators that you apply to a certain mode, right? It is to be associated with a certain mode, right? So that's why we give. So this is C, this is D. We give different operators because this is associated with the mode this way, and this is associated with the mode downward, right? Okay. But now we know, because of this experiment, we know that although the E field does not work as in classical, very well defined, it is nevertheless limited. The field of the single photon state is limited to a plane. That's how we know by this, right? Because this has a certain direction, right? And if our transmission follows this, that means our E field is limited to a plane, to a well-defined plane. And as this rotates with respect to that plane, the interaction gets stronger or weaker. Yeah. So now the mode, because of this experiment, we now know the mode has not only just the K, but also a plane. And you can say, and this actually have some significance. You can say this is the normal vectors associated with that plane, right? My E field oscillate in not in this direction, but in this plane. This could be the normal vector associated with that, okay? Or you could just say this is the because the plane because the plane must be normal to K, to the perpendicular direction. So, sorry, my bad. Yeah, the geometry looks okay. The plane I'm talking about is this. The plane I'm talking about is this. Okay, revolve around this axis, revolve around K. Okay, and this is the polarizer, right? And this is the polarizer angle. Okay, so we know the E field is restricted to this plane. Okay, and no, this is the single photon. By this experiment, we know that the E field is restricted to a plane. If this is my direction of propagation, this is my K, right? And I rotate my material in this direction, and I see a transmission following this angle. Okay, that must means so if this is the plane, that must mean my E field is restricted to this plane. Okay, and it goes like this.
So we know there's a plane, we know like
how to interpret it. We know there's a plane, okay, and now we can. This is for other reasons, but we know that the oscillation. Okay, I think this is good. We know the oscillation must, the E field must exist in the plane. There's another plane where the E field exists, and we know that that plane is perpendicular, must be perpendicular to the K vector. Okay, and that is due to some kind of gauge stuff. Okay, so there's another plane. That plane is perpendicular to the K, right? So now you have this two plane crossing each other.
And that's
yes, that's this.
And that's like the green one. The green one is kind of related to maybe related to K. Is that
right? The green one is given by K. The green one is given by K because the E field can only exist in this plane. And now we know, because of this experiment, we know that so it can exist here, right? But because of that experiment, we know that the E field must exist also on another plane that is defined by the polarizer, right? So the join of the two plane give you a line. Okay, and the and this line defines your polarization even at a single photon level. Okay, but again, what I'm trying to say is, since why can't we just define this through like in a classical sense? Because in a classical sense, you have a well-defined oscillation, and that oscillation always traces out a plane, right? And this is just kind of messy, and it's not straightforward. It's not straightforward that we will necessarily have a well-defined polarization and so on and so forth. So therefore, we need experimental evidence to show that this same polarization is still valid, even though we don't have a well-defined oscillation phase. Okay. And later you might learn that this is associated with photon spin. That's its ultimate interpretation. That's like you will think, oh, why? So since we don't have a well-defined oscillation, how, like, what does polarization even mean?
Today, or like today, if you said that that's related to photons,
Spin.
photon spin, then it seems that there's some theory for this.
Right. Yeah. What I'm trying to say is the fact that it has a polarization is not found through theory. It's like Schrödinger equation. You don't derive Schrödinger equation. Right, to fit your observation. Your observation reveals certain facts, and you try to modify, you try to like construct a theory that fit this observation, but you don't explain it. You see the difference? You see me wearing red, right? Today, you cannot explain why I wear red. You can make a story that I wear red, but you can, right? So I'm just saying that the fact that it, so maybe I should clarify that the polarization that we found for single photons is the same. Phenomenologically, it is the same as the polarization in the classical wave. But the physical interpretation is different because this is associated with field oscillation, and this is associated with photon spin.
I thought the theory of spin comes out very early. So
photon spin?
I thought like each particle,
like electron spin half?
Yeah. So do people suggest that photon doesn't have spin? I thought
they don't even know there's photon. They're not even sure there's photon. Remember, it takes so many decades of experimental effort. It's like a filter to figure out like what does single photon exist or not. If it exists, does it still have the polarization property like the classical wave? Does it still obey the beam splitting rules? Like how different is it from the classical wave, and how similar it is it to the classical wave in different measurement? So they need to find this. They need to establish all this fact experimentally, and then they can build a theory to kind of summarize their observation. So the theory is really just to summarize the experimental observation. And of course, from these little facts, if you summarize it and make it into theory, you can make a prediction for future experiments, right? And so, and as you make predictions and do new experiments, you find out that it might be even more peculiar than you have imagined. And at that time, you have to expand your theory a little more. And so that's how this iterative process is how quantum optics evolved. It's filled with paradox and puzzles and sometimes just drive people crazy. But yeah. Anyway, yeah. Thanks for the question.
What happens if I change the path difference to incident light?
Say again.
What if I change the path difference?
Path difference
Of the two incident lights.
Oh, you mean if I apply a phi here?
Yeah. Well, we observe the same.
Oh, you mean if I have single photon here, and I change the different
like a glass or something.
right. Yeah, that is a good question. I think that will not affect the result because you see here, if you do this, right, then this will be a global factors on the two photon state, and this will not affect the relative relationship. It will stay out, and we just this phi will be imparted here and here. Both of them will carry the same phase, but the 1-1 still will cancel. You see what I'm saying? Yeah. The subtlety of quantum optics usually can be solved if you work out the math. And sometimes the math is, I'm not a big fan of math, but sometimes a lot of confusions and misunderstandings are results of certain logic errors, and it's hard to figure out what that is unless you use the math structures. And from the math, you can it will become easier to identify. Oh, it is this term and this term that is cancelled, and that's why this is and this that makes this important. You can see why. From math is just another language that gives you a very logical description or logical. It kind of expand your argument in a logical way, so that you can examine each step and see where the error comes from, where the conflict, where the paradox come from. Okay. All right. So the conclusion here is through this transmission measurement, we know that there's some kind of polarization associated with single photon field. Okay, some kind of polarization, because the E field must exist on the plane that is, that follows this, right? So then there must be some kind of polarization exist for single photons, and that's an experimental observation. And during the break, Tin has some very good questions, and then I told her that it just so turns out that this field that this plane where the field exists, and the plane where the field must exist, because the field has to be in the plane that is perpendicular to the K. This will give you a vector or a line, and that defines your that line. That is your polarization. That is the polarization of this. Okay, what I'm trying to say is, the bottom line is, through Malus experiment, we know that mode is not only defined by the wave vectors, but also there's an additional parameter called polarization. Okay, so a mode is completely defined by polarization and the wave vectors, and And this wave vector, this polarization, is phenomenologically it has the same. It has the same direction as the polarization in the classical wave. It is just the physical interpretation of that is different. The physical interpretation of this polarization is the plane that this oscillation trace out. Okay, here we don't have a well-defined oscillation. Okay, so what is the physical interpretation of the polarization here? It turns out it is associated with photon spin. Okay. All right, so cool. Yep. So now we're gonna go to our second topic, delay choice quantum eraser. So what is delay choice? So this is the first. Eden. Next time, check the pens. 3 pens are not working, and I have very few left. So in the 70s, I think, even this is not working. Gosh. Wheeler. John Wheeler. So around the 70s, very famous, the PhD advisor of Richard Feynman. Okay, John Wheeler from Princeton University. So he has proposed, he's a theorist, and he has proposed a series of thought experiments. And those thought experiments are meant for investigating whether a picture of a photon traveling in space is valid. Okay, so this is the original. There are many versions of this, but one of the original versions called this. It's called delay choice experiment. So imagine you have a star. Now it's very far away from Earth, okay? And the star emits light, photons. Yeah? Earth is here, okay? The angular angle is very narrow because of the distance. So only a very small portion of light gets to Earth, right? However, in the galaxy, there are, stuff that can produce a gravitational lens effect. So for light that goes through this thing, it can be bent and redirect to Earth. The result of this is that in the telescope, you will see 2 images, one brighter, one dimmer, of the same star. And this is real. This is a gravitational lens effect. Gravitational lens. So gravity lens effect. Anyway. So this is a known experimental fact. Okay? Or this is like a observed thing. I'm sorry. Oh. Now Wheeler proposed. So if you take these 2 light, okay, before they hit a detection image plane, you have a beam splitter. You place a beam splitter, you collimate it, you collect the light, you collimate it, and you put it through a beam splitter, right? Such that there are 2 pathways. So either, this is a terrible drawing because I don't know how to, okay, so I guess we can draw this. So one goes this way, one goes this way. Okay? So this goes through and okay, good. So we have one beam that goes through and one beam that reflects. And we have one beam go through and one beam reflects. Yeah? So you can use a beam splitter and turn this to 4 beams because we have a reflected beam and a transmitted beam from each. So in total we have 4 beams, right? And then you can put your detection plane here. So instead of here, you move it to here. So pretty much like what we did with Hong and Mandel, you just arrange your detection scheme a little bit different. So it was like this direct observation versus so imagine this is your camera versus you put in a beam splitter and then you have the camera right behind it, yeah, on one of the ports. What would you see? Here, you see 2 stars, right? Now, after they are, collimated and then put into this, you see interference fringes. Yeah. And he argues that the 2 images that you see tell you about the particle property of the photon, because one photon is traveling this way and the other photon is traveling this way, and so they fall on 2 different locations of the image plane. Thus you have 2 images. So this result comes from the distinguishability of the 2 paths. One path gives you this image and the other path gives you that image, right? They are distinguishable, so you have 2 images. So this is distinguishability, and that is particle. So distinguishability means particle, right? On the other hand, if you just, get your device, so this is a collimator, and here you have a collimator, you just put your device in, that gives you interference. And interference is due to indistinguishability of the 2 paths. Indistinguishability of 2 processes that arrive at the same destination. Okay? So, and that is the wave property. Yeah. So his argument is the photon that has left this start, say a year ago or 10 years ago, if it is a photon, a particle in a particle form, it will remain a particle form until we detect it, right? It does not, they are so separated, right? It cannot switch between particle and wave. During its travel, right? So after the photons are generated and they have left the start and they have traveled pretty far away already, so say 1 year. So by the time they get here, it is 1 year. Okay? So that take the photon 1 year. So the distance divided by the speed of light is 1 light year. Okay? And then there's another year for it to reach here, to reach Earth, right? So on the time scale that we arranged our detections, the photons will already be quite separated, and then and kind of determined in a sense. So his question is, how come the fact that I arrange my detection apparatus differently will affect whether it behaves like a particle or it behaves like a wave? So this is called a delay choice experiment. I delay, but at the time that it was generated, I do not set up, I did not determine by which apparatus I will use to measure the photons, right? I wait until they left the source for quite a long time, for 1 year. I wait, and then I choose my detection apparatus, whether it is this direct detection or it is this. So I delayed my choice. And turns out the delay of your choice will give you very different result. One is with fringes and the other are not. One reveal the particle property and the other are not. So his conclusion is how you, and it's really a bizarre conclusion, how you choose the way you choose your observation, your observation method kind of affect, by simply correlating these two observations and that the photon is traveling, by simply correlating these two elements together, his conclusion is it appears that how you choose your observation apparatus will affect how it is generated, even if that happens in the past, whether it will be generated as a particle or it will be generated as a wave. Okay, so that's a paradox that he came up with. Yeah, that's called delay choice. And right. And later there's a variation of such an experiment. Okay, so the it goes like this. Later there's a variation, and what it is it says, okay, if I put a polarizer here and I set it to H state, yeah, and I put a polarizer here and I set it to V state, right? I could not even, like, the argument is simple. I don't even have to change this apparatus. I just change the setting of my, I can just simply change the setting of my measurement. So imagine you put a polarizer here and put a polarizer here, right? Then simply by setting this at two orthogonal polarization, you can wash out. You can wash out the now you don't wash out. You can kind of eliminate the interference fringes. And if you eliminate the interference fringes, then you see two images. Okay? And that's the particle property. So simply by changing this setting, you switch this between vertical or horizontal. You can switch between the two observation result. Yeah? So that's like another way to do Wheeler's delay choice experiment. Okay, you don't change this, you simply just have two additional optics attached to this thing. Okay, You change the settings. So now it is even more peculiar because by the single act of turning, or I can use this digitally, right? I can digitally rotate my polarizer. I don't even have to stick my hand into the experiment. I can digitally use a motor and I rotate it, and it appear that if I just switch to this, I see fringes. If I switch to this, I see no fringe. So I see particles, right? Yeah. Yeah, imagine this is a single photon experiment. So it builds up one dot at a time. Okay. So by changing this, the build up will either look like every time you have one photons, the build up will the final build up will either look like this or it will look like this. Okay. And this is called particle because the photon just like land on different positions and that's all. But this is called wave. It appears that there's certain correlation between photons landing here and there, right? Okay, so this is like a little variation of Wheeler theory choice experiment. Now, the paradox is if I, at this moment, if I add a third optics, if I add a third optics right before my camera, okay, my single photon detector, my single photon camera, and I can choose to either align this with H or V or something in between. Okay, so 45 means the 45 angle, something in between. So if I do H or V, I see particles, the particle picture. If I do 45 degree, I see the interference fringes. So in a way, I kind of erased. Oh, sorry. Particle means distinguishability. There's distinguishability, right, between two paths. And the reason this works is because H polarization label this path, or H polarization become associated with this path, and V polarization become associated with this path, right? So these two paths become distinguishable. Therefore, when they go through the beam splitter, one is V and the other is H, right? And the distinguishability kills the interference. Now, in the eraser, the argument is if I turn this continuously, then in some region, I will find that the fringe will be restored. If the fringe is restored, it means in this setup, it becomes the two paths becomes indistinguishable, right? That is to say that which way information is erased, is gone. Okay, so that's called quantum eraser. That's basically called eraser. You erase, what do you erase? You erase the which way information. Yep. Okay. So this is even more strange. By how you set up your first polarizer, you you can determine whether the particle travel as a light, as a wave, or a particle. Whether the photon travel as a wave or as a particle. And even after you do that, you have established the which way information. You have labeled the path of you have labeled the path so that it becomes like a particle. Now you can use another knob to undo what you have done here. Isn't that strange? Because if you think a photon, okay, as a particle, as an entity that travels through this apparatus, by the time it gets to here, by the time it gets to the detector, right, you will have already been established whether it travels through this path or this path. But just simply by rotating this my apparatus to 45 degrees, I kind of undo the effect on the labeling effect on the previous the previous labeling effect act on the path. Okay, so this all sounds very, very strange, and all this argument is to, like I said earlier, all this argument is an effort to invalidate the pictures of a photon being like a ball, like a bill ball, like a ping pong ball, travel either along this path or along this path. In the lab size experiment, it might be easy to imagine. It might not be hard to imagine that your photon can simultaneously exist in two paths, right? But on the astronomical scales, right, with separation so large, thousands of kilometers, with time separation so large, years, 10 years, it's really difficult to imagine that this superposition can still work. You see what I'm saying? It's really hard to imagine this superposition business can still work at this scale. Okay? So naturally, people would think, oh, yeah, sure. By causality, you know, when the photon, the photon must choose to leave either through this path or this path, right? Because they are so far apart. And then, and if it's on this path, then what I did here or what I did here shouldn't affect it, right? But it does. And if it's on, it is a very, very strange thing. Okay? So that's the historical background of delay choice experiment and also delay choice quantum eraser. And what qualified this quantum, this idea can be arranged in a realistic atomic experiment where you have, I'm going to briefly go over it, where you have two slits, two widely separate slits that kind of just separate the atomic being into two beings. Okay, and then you make it go through a RF cavity. Okay, and before the atoms enters the RF cavity, you excite it with a laser light so that the atom has, internal excitations. Okay? Now, right behind, so this is the exit. This is the exit. Right behind this RF cavities is a plane of 2 small holes. And the atoms that go through here and here. The atoms that go through these cavities will go through this the slits at the bottom, and the photon will go through. So this is first. This is 2. The photon will go through the first cavity. Will go through this slit at the top, and this will become a spherical wave, and then they will interfere. Give you an interference here, right? Now this polarized, this path labeling mechanism is achieved by just passively. You don't even do anything. Just passively put this cavity here, and the cavity will be tuned at a certain length that is resonate with this frequency. Okay, so that when the particles travel through it, it will emit a photon, 100% for 100% probabilities. Okay, so like when you do the this is like when you do the experiment with the MV center, right? You apply a pulse for a certain time, like 100 nanosecond, and at that moment, in between you don't know, but at that moment, at 100 nanosecond, you know for sure 100% you will be in the ground state. This is the same thing. You kind of tune the empty cavity in a sense that it will trigger by cavity QED. It will trigger the emission of the atoms 100%. So if the atom go through the upper path, upper cavity, you will leave a photon here. If we go through this, it will leave a photon here, right? So and if it leaves a photon here, then it must go through this slit, right? So this slit is lit. So later we can. So this is like a delay choice. Later we can open this box and see if there's a photon here, right? We can connect this to a detector, and later we can turn on this detector and see if the photon still exists. So we can, like right now, before our detection, we keep this off. We don't do anything. But the fact that it emits a photon and leave it in the cavity already labeled the path, and this will the outcome is that this will kill the interference fringes. Just in the same way that the price. This is just a simpler version. Okay, this is a more realistic experiment. Okay, and now the thing is, if you so how about this? Now if you gate, and this is a very peculiar part. If you gate your detection according to so you establish a coincidence. So if there is a photon emitted in this cavity, right? you turn on the detection on your screen of your camera. So if you gate the detection on your camera with the photon in the cavity, then you will restore the interference fringes. In the same way, if you get it with this, you will also restore your interference fringes. But the two interference fringes will be out of phase. Okay, one will look like this. So it has a dip in the middle. And the other will have a dip, will have a peak in the middle. Okay? So by sorting your detection according to this, you can restore interference fringes. Okay, and that's the quantum eraser part of it. Okay, so how does all this work? Okay, and I'm gonna go over, like I said, all these puzzles and all this paradox can generally be resolved if you have formulations of your argument. If you can formulate your argument mathematically, then it will be easier. It'll be easier to see where the contradiction comes from. Okay, it will be not so puzzling anymore. Okay, and this is the last thing I want to say, and then we're done. I'm gonna use that, but they are. Okay, let me just use this. Okay, I have two paths. Okay, so two mode. I have two modes, right? When I have two modes and then they go through a beam splitter and reach my camera without all these polarizers, this is what I have. Yes? And this will give me, I'm gonna use something called density matrix for a reason that will be seen later. Okay, I mean, of course I could do this. All right, these two states are not orthogonal. Okay, they're basically position wave functions. Okay, I'm just using K to represent them. They are not orthogonal in the sense that for each, here I am not summing the total probability. I'm examining the probability at a certain locations. Okay, so this gives me the interference, correct? Okay, now I'm gonna use something called the density matrix formalism, because later this will be a more natural language to use. So I want to start with this. So this is, like I said in the previous lecture, density matrix is a tensor product between two vectors. Okay, so so dot product is this. 1, 2, 3. Sorry, this is the column, right? 1, 2, 3. This is a row. 1, 2, 3. Right? So this is the dot product. 1, 4, 6. A dot product give 9. A dot product give you a scalar, right? It lower the rank. Okay, so vector is like a rank 0, rank 1 tensor, and scalar is a rank 0 tensor. Yeah, and the matrix is a rank 2 tensor. A dot product give you lower your rank, so you go from you make vectors, you turn vectors into a scalar, rank 1 to rank 0. Okay, but a tensor product. Okay, you see, I switched the position of this two. 1, 2, 3. 1, 2, 3. Okay. How does a tensor product work? A tensor product works like in the following way. You do this element by element. So 1 times 1, 2, 3. 2 times 1, 2, 3. 3 times 1, 2, 3. Okay. So this is the whole. This is the big element matrix. So this become 1, 2, 3, 2, 4, 6, 3, 6, 9. Okay. So a tensor product raise the rank. So in the direct notation, it's like you put it bottom to bottom or nose to nose. Okay. Tensor product is nose to nose, and the dot product is bottom to bottom. Okay. Butt to butt. Yeah. So that's easy to remember. All right. So this is a tensor product, and how and the algebra is the same as for scalars. So you just do distributions. K1, K1, K2, K2, okay? K1, 2, K2, 1. Okay? Yeah. And this usually has a diagonal element and off-diagonal elements. The diagonal elements are your eigenvalues. So that means the probability of finding a wave in, so this is x1, x2, x3. So it goes like this, right? Because this is x1, x2, x3, x4, right? So this element here means the probability amplitude to find a particle at x2. Okay. Now, so are this tensor. So are this tensor product. So this tensor product is just from K1. So the diagonal elements have the probability of finding K1. Okay. The probability amplitude of the K1 mole contribution. And this is K. So this, what I'm trying to say is, here you have diagonal elements. Here you also have diagonal elements, right? This is from path 1. I mean, all of them will contribute to this, right? Because this is a matrix. This is 4 matrix, right? So I am reading my measurement from the diagonal elements. So I need to know, like, where does this, so I have an element here, I have an element here that contribute to this. That is this and this. right? Are you following? Oh, okay, try to follow. And here you also have two matrices, and the diagonal elements also contribute to this. So, and that's these two terms. You see what I'm saying? Yeah.
I didn't understand how you put together the side 2 in this matrix, because this matrix is the what's the name? Not bracket, get bracket.
Yeah.
And I mean, there is no side 2 in get bracket. Is there?
Side 2. What is side 2? K2. Oh. Okay, what's the question?
I don't get how that one is contained in the tensor matrix.
Oh, okay. All right. This guy. So say, let me back up a little bit. If I want to find out the probability of detecting my particle at the position of x2, what do I do? x2, right? The probability of finding my particle at x2. So x2, I put x2 everywhere, right? So this will be x2, 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 right? Yes? It has 4 contributions, right? 1 contribution from this state, 1 contribution from this state, right? And I have also the cross terms, which is the interference between these two states at the same location. Okay? All right. Now I'm using a different formula then. Okay? I'm using a different formula then, cotensor product, density matrix. And here, what I'm trying to say is, if this, you can see this is a column vectors, right? Because it is constitute of 2 column vectors. So of course it is a column vector, right? So just by not expanding it, just by this, you know that it will become a matrix. And the second element in the diagonal will be this value. Which is this. Okay? So I'm just trying to teach you how to read a density matrix and associate it with the usual representation that you use. The point is, you look at the diagonal elements. That is your measurement result. Okay, you look at the diagonal elements. Okay? Now, so if I want to look at the diagonal elements, then since I can expand this by its component vectors, right? I have 4 tensor products, 4 density matrices, right? Just from this direct expansion, I have 4 density matrices, and each density matrix will have a diagonal elements here and there, and the second one of them will contribute to this number. And I'm saying that here the density matrix is this term. Okay, let me label it. 1. This is 1. This is 2. This is 2. This is 3. This is 3. This is 4. This is 4. Okay? So what I'm trying to say is that the interference that you typically see is from the density matrix of this 2. It's from this 2 density matrix. It is not from this 2 density matrix. These 2 density matrix correspond to the DC term. the AC term comes from this density matrix. Okay. All right. This is important because in the discussion of delay and quantum eraser, it is crucial to have this formalism. And since this is our last lectures on quantum optics, it is a little hard. So I hope you don't mind. Hey, but if you figure this out, pretty much you can understand all the future quantum literature that you read. Okay, this is like the best it can get. The most difficult, the more. This is as difficult as it can get. That's what I'm trying to say. Okay. So if I have no, again, this is my two path, right? And this is my polarizer. This is a K1. This is a K2, right? And I have this, and I have this, and I have a detector here, right? Or my camera. Okay, now if we label the path with H and V, okay, then the state become H and V, right? The path is labeled by the polarization. Okay, so earlier you could say that polarization is the same. They are both H. Here you can say that the polarization is the same. They are both H, for example, and the H can be factored out, right? But now I give them different polarization. I allow different polarizations to go through, right? So I label the two paths differently. Yes? Okay. And if I would just do this, again, if I would just do this again, you will see that the DC terms are intact. But the AC term now have this, right? Since these two are, the two states are distinguishable, what does it mean by distinguishable? That means these two do not overlap. That's distinguishability. So your distinguishability is now mathematically expressed as H dot V is 0. Okay? So the overlap between your labels is 0. If the overlap between your label is not 0, it's finite, then you can still have some interference. And that's called partial coherent. Okay? If the label of your path become in another language, you can say this is entangled state. You can say this is an environment. The environment is interacting with your system, and your environment entangled. This is the environmental state. Okay, so you can just interpret this in another language. Okay, the environment is in one state if you are in path, if you go through path 1, or if you're in state 1, and the environment is in another state if you go through state 2, okay? So the two states are labeled. Okay, now this environmental state can be distinguishable or not distinguishable. If they are distinguishable, which means the dot product is 0 between these two environmental states, then it will completely kill your interference. Yeah? And in the decoherence theory, this means complete decoherence. So this becomes incoherent. Your coherence is lost by entanglement with the environment. But if this is partially, this is non-zero, but this is low. Okay? So this is partially distinguishable. This is a then partially distinguishable. Then you can still have some interference left, right? But your fringes will be, the visibility of your fringe will be less, right? Because how do we calculate the visibility? Well, we kind of compare it with DC, remember? Okay. So anyway, so what I'm trying to say is that the coherence process also works like this. Just in this case that we have like fully distinguishable labels, therefore it kills the coherence completely, okay? But this can be cast in another language in terms of the coherence and environmental entanglement. And there it's more natural to discuss whether the two environmental states are fully distinguishable or partially distinguishable. It's continuous. If it's partially distinguishable, then the entanglement will not be so detrimental, and we will still be left with some kind of interference fringes. Okay? All right, so that's just something at the side. Okay, but here for our purpose, it is distinguishable, so it's dead. Okay? And this is the delay choice. So this is the delay choice part. We in the delay choice is that the path are entangled with certain labels states, and when those certain labels that are distinguishable, it kills the interference. So this is where this delay choice comes in. Okay, to undo the effects of this labeling or entanglement, there is this quantum eraser, right? So how does quantum eraser work? Oh, by the way, let me write this in this language. Okay, so I have this 4 states, right? K1, K1, K1. Okay, and now K1 is, so I have H1, H1. Yeah? K2, K2, V and V. And K1, K2. Okay. when we make a measurement, when we make a measurement here with this polarizer set at the initial H polarization, that is when we apply that, it's called partial trace. Okay, it's called partial trace, and you all right, sorry. So this is the full system Hamiltonian. Okay, I'm going to use the environment language again. So these are the environmental state, right? This is the environment density matrix. Yes? But when we make a measurement, we measure the particle only. Oh, sorry. I'm sorry. Forget about this. When we make a measurement, we do not distinguish their states, right? We do not this thing cannot tell whether it is H polarized or V polarized, correct? So that degree of freedom is the information of that degree of freedom is disregarded. Yes, and this is analog to this environmental entanglement when we make a measurement of our quantum state. We don't have information about the environment, right? So if it's entangled with the environment, however, we cannot track that. So what we can do is to only measure our system of interest, right? So when we are forced to leave out some information, okay, we will have a reduced density matrix. Okay, reduced. So this is the full density matrix of your state and your what do you say, environment. Okay, this is the full density matrix, and you can see that the coherence part, it is still here. It is not gone. This is not zero. Okay. Yes. I mean, you have zero for dot product, but the density matrix does not have zero. 1, 0. If you do dot product, 0, 1, and 1, 0, this is 0, right? But if you do tensor product, is this 0? No, this is not 0. Okay? So I'm just saying that this is not 0. Okay, so in the full state, in the complete state, you still have your coherence. Okay? The coherence are not killed like this. So how does this work? Because I know from my experience that the coherence will certainly be killed. How does this work? How does it work with the density matrix? Okay, so what I'm trying to say is, so this is a full density matrix. But if we are forced to leave out some informations, then we will have to deal with a reduced density matrix. Okay. And the reduced density matrix is, so say this is K, okay, because we only detect K, right? Then we will have to chase out the polarization state or the environment, okay? And how does this work? this operation, this partial trace operation, works like the following. You do this. You applied all the possible states of your environment on your tensor pod, on your density matrix, and you sum them. Okay, you sum them. Okay, so the sum is the trace part. Okay, and why is it called partial trace? Is because if it's a full trace, if you do a full trace of the density matrix, you have to do the same thing for all possible states, including the case. So that would be this plus this plus all the case. Yeah. Oh no, sorry. Not all the case, all the x. Because k is in x. Okay, this is the full trace. Okay, this is the partial trace because it's only part of it. Okay. All right, so when you do this, you see that you put this here because this only talks to the environmental state, only talks to the environmental state, right? So you put, if you put h here and h here, this is 0. Same here. Put h here, this is 0, right? You put h here, this is 0. So only this term gets picked up. Yeah? And you're left with the density matrix of the momentum states. Okay? The same here with VV. You do VV here, you pick up KX, and the rest is discarded. It's gone. Yeah? So, you see, this is the DC part of it. This corresponds to the original density matrix, to the DC part of the original density matrix, and the interference part is gone. Yes? So that's how, this is how the delay choice, or the which way information how delay choice is manifested, or how which way information is manifested in the density matrix formalism. Okay, you need to do partial trace. Okay. Okay, now it comes to the final thing. If we do if we put another polarizer here, and this polarizer, the function of this polarizer is to break, is to separate the H and the V into two subsets. Okay, this is kind of tricky. It's hard to explain, but this is kind of tricky. So this is your H, this is your V, right? And this is 45 degrees, right? So H and V can be separated. They can be decomposed into another basis. Or in other words, they can be separated into two subsets. One subset have projections on A, and the other subset have projection on B, right? So A and B, A and B. The only difference is there will be a minus sign. So one is symmetric, and the other is anti-symmetric. Metric. Yeah. Okay. The reason I want to talk about this is because when you replace H and V with this, then you can have this become a little different. This become K1 plus K2 A and K1 minus K2 B, right? Now, if I now take the probability, then I will have in the DC term K1 plus K2 and and here I will have K1 minus the K2. Yeah, and and here I will have cross terms. Cross term will be K1 plus K2 times K1 minus K2 A and B, and this is its conjugate, right? Still, this cross term is 0. This is 0 because A and B are orthogonal now, right? But the DC term that we left has interference in it. However, we need to be careful here because you see here we have K1, K2, we have K1, K2, K1, K2 with a plus sign. Yeah? But this guy here, we have K1, 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 K2, K2. K1, K2. K2, K1. We have a minus sign. Yes? So therefore, the interference is still 0. It is still killed, washed away, right? But if we do coincident measurements, we gate this with A. Okay, so we do coincident measurements, we get this with A. Yeah? Then we'll only have this term left. We will not have this term. Okay? And if we gate this with B, we'll have this term, this interference, but not that term. See, but the phase is 180 different. So the interference, if we do not use coincident measurement, then the two interference with opposite phase will cancel each other. But if we use coincident measurement, then we post-select from our data a subset, the A subset, and the interference can be restored or be reserved. Okay? Preserved. No, sorry, not reserved. Preserved. Then the interference can be preserved. Okay? And in formally in this language, we will do what we do. What I'm trying to say is, if we do projection measurement, then it is no longer a partial trace. It is no longer a partial trace, and the partial trace means we disregard the environmental information, and we basically sum up all projection to the environmental state together. Okay, but if we do projection or coincident measurements, then we post-select a subset from the measurement, and the inference can be restored. And this is the quantum erase. What I'm trying to say, this is projection thing here. This is the quantum eraser. This is why the quantum eraser works. Okay. All right. So anyway, I know this is a lot to take. This is recorded, so if you want to have a further reading of some introductory quantum optics textbook, and then come back to the lecture, it will help your understanding. If you want to, you can always come back. But I want to lay this out here for you, just so that later you will have an opportunity to come back and figure out what this is. This is difficult, even for very advanced graduate students in quantum optics. This is difficult. So don't feel bad if you feel like you are completely lost. It's normal.
Shouldn't that be tensor product? Like when you try to multiply to check. Or else I couldn't think of the
Where?
K
Here?
K1 and H. Because if K is a matrix of n by n times 1.
Uh-huh.
And I couldn't think of how to like figure product between n times 1 and
Right, this is this is a tensor product, yes, correct. But this is a tensor product between two column vectors, not the tensor product between a column vector and a row vector. So this only makes the tensor product make the vector longer. So for example, if this is a 3 position, right? x1, x2, x3. So this is a 1 by 3. And this is a 1 by 2, right? Together they become 1 by 6.
1 by 3. And so when you write the
Yeah, I'm saying if I just have three position state, then by 1 by the first one is a row.
Oh.
Okay, and the second one is this is the matrix notation, right?
Oh.
So this for example, this one is called 2, 3, element 2, 3.
Oh.
So if you have a 1 by 3, then you have 1, 1, 1, 2, 1, 3.
If it's like this, isn't it 2 by 3?
If it's like this,
Yeah, because it's 2,
Yeah.
3, so it's
yeah, this will be a 2 by 3.
so.
Oh, sorry.
Yeah, so
2 by no. This will be 2. Okay, you're right. You're right. I'm sorry. You're right. I got you. Yes, yes, yes. 3/1. Thank you. Okay, your math is better than mine. So 3/1. Yeah, but the same. So 3/1, 2/1, and this is huh?
I'm wondering, like, how does psi A look like?
This one?
Like, after you do the tensor product, how does it?
Oh, you mean how does the projection work?
Yeah, I want, because I try to imagine, like, how does the metric cell look like?
Okay. That's a good question. So I guess you're saying what you're saying is this is a 2/1. This is a 2/1 vector, right? And this is a 6/1. So how can I do tensor product with it?
Yeah, so that's why we are using tensor product, right? So
You mean this?
I mean, if you try to do the multiplication between two cats, then you have to use
Okay. Yeah. All right. So the technical difficulty that you have is, so usually when we do projections, this is really an I times A. You see what I'm saying? So this is the regular 2/1, and this will be 3/1. 1/1. And this will be 6/1. Yeah. So there is an explicit. So when we do a dot product for some state that is a tensor product, right? We usually specified the variables of interest, and the other we just kind of implicitly assume that it is the identity. Okay. Yeah. So yeah, that's a good question. So anyway, this is just technical issues. All right, guys. So we have everything written down and recorded. If you watch this video 10 years later, I'm sure it'll become clear to you. But the reason I want to put this here is because you don't get to learn this in quantum mechanics 101, okay, or quantum mechanics 201, or even quantum mechanics 301. You don't get to learn this unless you're doing research in this area. And the purpose of this course is to give you a survey of what's out there in quantum optics and quantum mechanics, to help you have a map, a little map. Even you don't understand everything, you have a little map. And through the lab activities, you have some feelings, you have some experience of this. So you know they are there. You don't fully understand what they are, but through your experience, your life activity, you can get experience with it, to develop some intuitive feeling about it. That's the purpose of this course. And I hope that it's my personal hope that this experience will help you in the long run. You might not know how to do the math now, but 5 years, 10 years later, if you happen to work with a company or a research group that deal with quantum stuff, right? And at that moment, you want to come back to your old lectures. I'll be pretty old by that time. Then I hope that at that time you will have an easier time. You will not start from zero. You will have an easier time understanding these advanced materials. Okay. All right. Now we have quiz time. We're running out of our time, so I have actually 4 quiz problems, but we're running out of our time, so I'm gonna choose just maybe one. Is interference signal. If interference signal is lost because of entanglement, can it be possibly restored? Okay. A very succinct but not straightforward question. Okay, read the question again. If interference signal is lost because of entanglement, can it be possibly restored? All right, please get up and line up according to your choice. So we have everyone yes and one no. Great. Tin, would you mind debate with Clement? That's awesome.
I haven't done the manual.
Which manual? Which is manual? Full lab manual?
No, only for the last lecture, quantum relation.
Okay.
You should restore.
Oh, I see.
Even though we didn't see that restore for the manual stage.
Okay, I see. How about she? Can you give a convincing argument that is more than one sentence?
I think this interference signal we lost from the angle because have so many data that we can figure out the discovery of them. But as we select the condition of the data, they will show it those it will be selected and showing their physical interference. And after that we can see the interference. I think it's the short answer for me.
Okay, thanks. Clement, tell him why he's wrong.
I wouldn't know what's wrong.
I mean, he chose a different side from you. So he must be wrong. And in your lab friend, in your observer friend, he's wrong.
I don't know. I don't know how to be wrong.
So you think you're wrong?
Could be, but like I don't.
Okay, how about Han? You want to try?
I'm really not sure. But just now, teacher described where initially there's interference. After that, it puts the interference disappear. After that, put another polarizer and interfere. So I'm not sure if that same with the statement outside the space. That seems pretty convincing. I remember the experiment. I remember the drawing.
Switch now though.
But like,
Oh, okay, great.
but I only remember the switching the V and H horizontal thing, and then it goes from like particle to wave. Yeah, And I also remember that like on the bottom left, he added another lens. Yeah. But I'm not sure like what's the effect of that lens. That's why I'm on no, because I only remember that it can be lost because of the
Yeah, you think it can be lost, right?
Yeah. But
You're certain it can be lost.
yeah, yeah.
Uh-huh.
I'm sure that it can be lost, but I'm not sure if it can be like reversed. Yeah.
Okay. 10. Convince Marlin to come back to your camp.
So there's because of the horizontal and vertical information that making that lost the interference signal, and after in the experiment that you described, you can add back the polarizer and add back the environmental term, and then making the putting, because previously we were trying to I mean, I haven't convinced myself. I'm convincing myself
by the menu.
Yeah, and I saw I don't have the complete logic of the math one, so but I just believe that that's environmental is information is something we can control, so we can like at certain conditions, maybe it's at certain angles, we can control it, and then we can make it to last the signal, and we can also trying to make the
possibly
try to make the entanglement come back by controlling the which way information, and also it's the at horizontal and vertical component. I think I'm lost in my statement.
That's all right. That's all right. You're making statement. That's better than making no statement. Anybody want to make a statement?
I switched because I got unsure of the phrasing of the question, because like my reason for standing on the yes side was your argument, but when you told me my argument, I just realized that I mean, it says if the interference signal is lost because of entanglement, and I mean, it was in the experiment, it was lost because we watched it. So I'm not sure if that's the same thing. So that's why I switched.
Okay, great. Mark, you want to say something? Want to join the party? Everybody's saying something. No, I think there are some words. Q, you want to? Entanglement is not real. No? All right. Yo? Who? Just like who? Oh, Tim. Okay.
If you choose some quantum number to label the path or the lines, so you can just simply or just say that they are it has some entanglement between the path and the particle's weight, path and the polarization. So if you just ignore the information of the polarization, it can be just like the partial trace.
Mhm.
So you can get the information about the interference between two paths.
Mhm.
Just like some feeling like that.
I'm feeling
Yeah.
good. Good feeling. Good. Great. All right. Thank you. So now everybody has altered their opinions. Let's reshuffle again and see if we have more vote on the other side or this side. Okay, move or not move. It's okay. You don't have to move. I give you 10 seconds to consider. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I would say this will give you like a 5-point bonus, would you guys please?
5-point bonus, I'm gonna change. We're trusting Manny.
Okay. No, I'm not gonna do that. But so nobody's changing positions. All right, great, cool. Okay, so the answer is yes, and it is the one thing you need to remember from all the things we just talk about. Your interference, that chunk of thing, is not lost per se by entanglement. It is, I mean, the coherence is still there, right? You've seen the density matrix. The entanglement does not destroy coherence, right? So it does not destroy interference. However, entanglement, what entanglement does is it kind of produce a second interference pattern that has an opposite sign. Okay, and if you do partial trace, so that which means you disregard the environmental state and just collect everything as a result of interference, as a result of detection, you just collect everything. Then the positive interference will cancel with negative interference, and so the interference will be gone. However, if the entanglement is trackable, not all entanglement is trackable, right? In the experiment that we designed, you know, with the polarizer and the RF cavity, those entanglements are trackable. The information are there for us to either consider or disregard, right? For those, you can do post-selecting or coincident measurements to pick up only the positive interference or the negative interference, and you'll be okay. And that's how you restore interference signals. But if you don't do that, if you don't do coincident measurements, if you don't post-select your sets, your subsets, you just put all the subsets together, then the positive will cancel with the negative. So it's not like the interference is completely gone. It is just there's a different version of it being produced as a result of entanglement, and that has a different sign, and they cancel. If you can separate them by coincident measurement, if you can, then you can restore your interference, and that's the effect of quantum eraser. That's basically the spirit of it. Okay, environmental. So in the controlled, so this entanglement business is very tricky. In the controlled environment, you can control all the informations. So you can kind of disentangle, right? You can separate by coincident post-select. So you kind of disentangle. But if it's like really just interacting with the environment, if the environment is not well isolated, and your particle is interacting with, say, materials, and there are like so many degree of freedom, so many lattice and nuclears and right, like a lot of things on the surface, and your material is talking to like thousands of electrons in the material. You cannot track that, right? And then you are forced to do partial trace. You cannot do coincident measurement. You cannot do like projection measurements, and then you are screwed. The interference will be lost. lost in the sense that the plus and the minus will cancel each other. The interference pattern as a whole is still buried there somewhere. It is not like destroyed. Okay? So that's your final lectures on quantum optics, and this touches upon the matters of entanglement, decoherence, and a lot of fundamental issues. So I hope that this somehow can stay in your brain in the corner and become useful someday for you. All right, let's move to the lab and do lab work.